There are several steps to hypothesis testing. Section 4.1 covers what you do at the beginning and the end, setting up the hypotheses and then coming up with a conclusion. Section 4.2 covers how you compute a p-value, which is essentially the middle part. A lot of this stuff would be very abstract without an example to work through, so that's what this ESP example is for, just to have some concrete pieces in here. The way that this works, this setup, is that you have the 5 Zener cards with the different symbols on them. And what's going on in the picture is that the girl on the left is focusing on one of the 5 cards, and the woman on the right is supposed to telepathically figure out which card the girl is focusing on. And since there are 5 cards with different symbols on them, it would make sense that the population proportion of correct guesses should be 1/5. From Chapter 3, we have the idea of sampling variability, which is that second bullet point. That's going to factor in pretty heavily in hypothesis testing. The reason that sampling variability is going to factor in pretty heavily is that you use sample data to assess some claim about the population when you're performing a statistical test or a hypothesis test. What you would end up doing with the ESP experiment is that you'd have to use sample data, maybe a bunch of repetitions where the woman tries to guess which card the girl is focusing on, to determine whether the population proportion of correct guesses is likely higher than 1/5. Because if you have evidence that the population proportion is higher than 1/5, that would be evidence supporting the idea of ESP. In a hypothesis test, there isn't a single hypothesis. In fact, there are 2 that are competing statements. The null hypothesis is a statement of no effect, no difference, or no change. In the ESP example, it would be that there's no such thing as ESP. The alternative hypothesis, the competing statement, that is a statement of change, or that there's some difference, or that there's some effect. That's effectively what you look for evidence of. You look to see if there's evidence in favor of the alternative, which would be the same thing as evidence against the null, when you compute a p-value, which is what we're going to do in the next section. The other part that's on here is the notation. The notation for the null hypothesis is an H with a subscripted 0, read either as H0 or H sub 0. Then the alternative hypothesis, A for alternative in the subscript. So H sub A would be the way that that's typically said. Generally, the way that a hypothesis test works is that if your sample data contrasts quite a bit with what's in the null hypothesis but matches up really well with what's in the alternative, then maybe that's where you would say, okay, it looks like the null is wrong and it looks like the alternative is probably correct. And as far as the setup goes, the hypotheses are always about parameters, never statistics. The symbols that go into your hypotheses should be p's and mu's. There's no point in having a test about a statistic, so about a p-hat or an x-bar, because you know what those values are. The idea of the test makes sense for something that's unknown. So the things that would be unknown would be population measures. Symbolically, always p's and mu's in the hypotheses, no p-hats, no x-bars. And then for the ESP experiment, for that example, if p is the population proportion of correct guesses, then symbolically, this is what the hypothesis should look like. Since the null in general should be a statement of no effect, no difference, here it would be no such thing as ESP, so the population proportion of correct guesses is 1/5. Then the alternative, the competing statement would be there is such a thing as ESP, and if that woman has ESP, then her population proportion of correct guesses should be higher than 1/5. So that's how you get that symbolic alternative. One other thing that goes along with this, I know that some people get kind of bothered by this setup where not every possible value for p is covered, because what about values that are less than 1/5? Where do they fit in here? They actually fit into the null. The common way to write out the null hypothesis now, which is how our book does it, so therefore that's the way the homework would do it too, is just to always set up the null as parameter equals some number. But when you have a one-sided alternative, by which I mean an alternative that has a greater than or a less than in it, the null could include the opposite direction, and that would be okay. So here, it would be okay to write the null as p less than or equal to 1/5, if you wanted to write it that way, so there it's explicit that those values would also be covered. That's not the way our book does it, but if you want to do it that way, like on a lab, that's perfectly fine. That's, in a way, the older way of doing it. The older textbooks used to do that, but you don't really see it too much anymore. The way that you write out hypotheses. Basically, your alternative needs to have some kind of strict inequality So either a less than, a greater than, or a not equal to. And then if you're going to follow along the way the book does things, you're just going to have an equals and a null. Although there are scenarios where it would be okay to have a less than or equal to or greater than or equal to. So the main points, strict inequality in the alternative, and the kind of strict inequality that you end up with would depend on the context of the problem entirely. The other thing is when you're writing out hypotheses, even though the convention is to write the null first and then the alternative, I actually think it's easier to come up with the alternative first, because the inequality that you need in the alternative will be dictated in the wording. And if you write the alternative first, then to back solve for the null, basically all you have to do is replace the inequality with an equal sign, and you have what belongs in the null hypothesis. So I think that's actually easier, even though it might be counterintuitive to do it backwards at first. For this example, comparing the effectiveness of two methods of foreign language instruction, if you don't know what those are, the grammar translation method is the one where, I guess if your base language, if your first language is English, it would be something to the effect of, this word means this in English. And you'd learn the vocabulary that way. With the direct method, you never speak in your first language. Everything is done in the target language from day one, which seems like that would be a rough first week, but that's what that is. In case you're wondering what those are, that's what they are. And then the thing that's being compared is average scores on a comprehensive exam. Then the third bullet point, what are the appropriate null and alternative hypotheses to see if there's a difference in mean exam score? If you try to get the alternative before you get the null, the key word is difference. That's what dictates the not equal to in the alternative hypothesis here. There's no specified direction, like is there evidence that the average score for grammar translation is higher or direct method is higher? That's not there. There's no specified direction. That's how you get difference. If there's a specified direction, then you'd use that. But when there isn't one, if it just says we're looking for a difference in general, you got to cover both directions that a difference could happen in. So you get the not equal to there, and it's a difference of means. So one population mean is not equal to the other. The subscripts are there just to differentiate them. I guess if you want to make that a little more descriptive, I guess you could do it as mu sub g and mu sub d or something if you wanted. And then the null would essentially look like what you've got for the alternative, just with an equal sign in it. You could also write the hypotheses for that example like this. At this point, writing it this way probably looks a little weird. Certainly these are equivalent statements. All I did was subtract mu2 from both sides in both hypotheses. So they're equivalent. This type of setup is going to make more sense in Chapter 6 than it is right now. But for right now, if you did want to do it this way, if this is a thing that you've done before and this is what you're used to, this is all right. A couple of other examples. That first bullet point, again, the key word is differ. So no specified direction, so you need the not equal to in the alternative hypothesis. This one's a difference of proportions, right? The word proportion is right there in the wording. So since it's for men and women, that's how I got the M and the W for the subscripts. I guess you could do that with ones and twos if you wanted. There's certainly nothing wrong with that. The one on the bottom, the key phrase for putting the alternative together is the less than. That's how you get that inequality, right? I mean, that's a direct translation of the verbiage into symbols. It's for a single mean because we want to see if the average amount of sleep is less than 7 hours. So mu less than 7, that's what we're looking for evidence of, so that's our alternative. And then the null would just be mu equals 7. If you wanted to write that as mu greater than or equal to 7, that's okay. This is kind of wordy, and there really isn't a way to shorten this up, unfortunately. When you have a statistically significant result, this is the scenario where you'd say, okay, it looks like the alternative is probably right and the null is probably wrong. And when that happens is, under the assumption that the null hypothesis is true, the thing that we're getting out of our sample looks really bizarre. To make that a little more rigorous, under the assumption that the null hypothesis is true, the sample statistic that we're getting is very unlikely to occur just by random chance. So it would be really unusual under that assumption. And that's where you'd say, okay, well then maybe that assumption, whatever's in the null hypothesis, is wrong. That's what it looks like. That's ultimately the way that this works, and the thing that's on this slide is essentially the linchpin of how section 4.2 works when you compute p-values, but that's also when you're going to get a statistically significant result, where you have something that's very unlikely to happen by random chance showing up in your sample. So when you get a statistically significant result, you get a nice strong conclusion. That's where you say, okay, it looks like the null hypothesis is wrong, looks like the alternative is right. However, if you don't have a statistically significant result, you end up with an inconclusive test. To make this slightly more concrete, we can run through it with the ESP example. Let's say we have a statistically significant result there. That would mean that we had a sample proportion big enough to where it looked like P, the population proportion of correct guesses, was really above 20%, or 1/5. So we'd say that the sample proportion is so high, it's unlikely to happen just by chance. And so that means that we have evidence that P is likely higher than 1/5, which would be evidence supporting the idea of ESP. However, if we don't have a statistically significant result, the conclusion that you get is a lot weaker. What we'd say is, well, our sample proportion could easily just happen by chance, so we don't have enough evidence to conclude that ESP exists. The trap here is to say something that's a little bit too strong and say, well, then we should conclude that P equals 1/5. No, we shouldn't. You really just can't say anything one way or the other. Saying that if you don't have a statistically significant result, then that means the null is true, that's a logical fallacy. That's a proof by example. Think about it this way. Let's say that this experiment here with the Zener cards and that picture in the upper right, let's say that's going to be repeated 100 times. And let's say that the woman on the right side of the picture is correct 22 times. That's not going to be far enough above 0.2 because that sample proportion is 0.22, right? That's just a little bit bigger, and the sample size isn't gigantic. So that's not going to come back as statistically significant. You wouldn't be able to conclude that P is greater than 1/5 from that, but you also wouldn't conclude that P equals 1/5. Not if P had is 0.22. That doesn't make any sense. When you don't have a statistically significant result, you end up with a conclusion that's a lot weaker, but that's just the nature of how this works logically. As far as having a statistically significant result is concerned, effectively there are two components. There's the difference between whatever your sample measure is and the value that's in the null hypothesis, but also the sample size is going to factor in because with a bigger sample size there tends to be less variability, so that's also going to be in play here. That's what's going to come up in this example. So suppose your current mutual fund manager has an average return on investment of $12,500 a fund, and a competing manager wants your business. So mentally, where would you start negotiations? Well, you'd say, the only way that I'm going to switch is if it looks like the competing manager is better. Certainly you wouldn't switch if it looks like the competing manager is worse. Or the same, right? If there's no evidence that the competing manager is better, then you'd say, well, if I switch, then I'm just creating a bunch of extra work for myself in that process of switching, and that might be all that I'm doing. Those would be your hypotheses, where you're looking for evidence that the competing manager is better on average. I guess here mu is the ROI for the competing manager, because you want to see if there's evidence that their average ROI is bigger than 12,500, because that's the only way you're going to switch, if there's a lot of evidence supporting that idea. So if the competing manager shows you a big portfolio, 200 funds, and the average return on investment is 35,000, then you're going to switch. Right, 35,000 is a lot bigger than 12,500, and that sample size at 200 kind of adds legitimacy to it. Right, you say, well, that's not just a fluke when he's got 200 funds, and that's what the average is. However, the second bullet point, the average is slightly above 12,500, and then only 6 funds. Yeah, 12,525 is bigger than 12,500, but only by a little bit, and that sample size is really tiny. That's one that you're not going to consider switching. And this example is here to kind of illustrate the same concept. So the probability of a player winning a hand of blackjack is about 0.46. Player wins 3 times in 5 hands. Yeah, that p-hat is 0.6, which looks like it's a decent amount bigger than 0.46, but the sample size is only 5. So you think, sure, that's going to happen pretty regularly. And it does. The chance of getting a sample proportion of at least 3/5 when you have 5 hands, 42.5%. That's not uncommon. That's going to happen pretty frequently. The next one, the second bullet point, 190 wins and 400 hands. Now we've got a decent sized sample, but our sample proportion's only a little bit bigger than 0.46. That's not that weird either. The likelihood of getting a sample proportion of at least 0.475 with a sample size of 400. 0.29, so 29% of the time that's going to happen. That's not that weird. 377 wins and 650 hands. Here you got a big sample size, and the sample proportion is quite a bit bigger. 0.58 is quite a bit bigger than 0.46. That one would be weird, and you can see it in that likelihood that's in scientific notation. Decimal point 90 is 566, right? That's a tiny number. Both things are happening there. You got a big sample size, so there's not going to be a lot of variability from one sample to another, but then your p-hat's huge. That's one that would look weird, but that has both things happening, right? Big gap between p-hat and the 0.46 and a big sample size. However, you don't need both of those things to get a statistically significant result. Typically, the cutoff, even though I'm getting a little bit ahead of myself, this is really section 4.2. Typically, the cutoff for having a statistically significant result is that thing that I'm listing as likelihood for right now, when that's less than 0.05. So both of these are going to fall into that category. That first one, big sample size, the p-hat really isn't that much bigger than 0.46, but here it's that idea with a bigger sample size, you're going to have less sampling variability. So then, in a relative sense, that makes that 0.5 kind of big, and you end up with a likelihood that's relatively low. The last one is in there to dispel a commonly held thought, which is that if you have a tiny sample size, there's no way you can get a significant result. That's not true. You can have a statistically significant result with a tiny sample size. You just have to have a really extreme statistic. And that's what's happening here. 20 wins and 20 hands, you can't get any more extreme than that. So p-hat is 1, and that's very unlikely to win 20 hands in a row. So the likelihood of getting that sample proportion, again, we've got some scientific notation. I guess that's a decimal point 6 zeros and then a 1 and then an 8. That's why I stuck that in there, just to point out that there is that kind of reflexive thought to say, well, if you have a tiny sample size, then that's not really going to give you anything. A lot of times that's true, but you might get something if your sample measure is something that's really out there, something really extreme like it is here.